So the last speaker this evening or this morning is Bing Wang. He's associate professor at Beijing International Center for Mathematics Research since 2014. And his research interests cover several topics, including theory and application of wavelets, image processing and analysis with medical and biological applications, and deep learning. So his talk today will be on learning to solve PDEs with hypernetworks. Please, go ahead. Thank you.
All right, thanks for the introduction. And as you can see from the title, it has nothing to do with image processing and or wavelets, maybe. Okay, so first of all, I'd like to thank the organizers, Professor Jin Chaoxue and all the, and John and everybody at PSU to put this together to make this happen. I know it's not been smooth. We originally thought that we could all meet together at PSU and then talk face to face. But I guess it's also cut the travel, because international travel can be really painful. I think this way maybe it's an easier way for everybody to talk at this difficult time. So this talk has it's composed of two of our work. One is from last year, and the other one is from this year, on solving PDEs using machine learning. So I will start with my talk with a brief motivation, which is also closely related to what Weinan had talked about early, today, or actually, the second work is a joint work with the Professor Qin Jiaoxu. Well, not because he's the organizer of this workshop, is because I really like this this work. Okay. So a overview. We all know that deep learning has been a great success. Otherwise, we wouldn't be here. But there are still a lot of pending issues. There are a lot of issues, but I will just mention a few that I care the most. The first one is the generalization of training algorithms. Not just me. I think a lot of effort has been made to analyze why stochastic gradient algorithms can generalize so well. And another topic is called model robustness, which includes adversarial robustness. And also the robustness in terms of distribution shift, which is in a sense is more general concept, because adversarial perturbation can also be considered as a distribution shift, but it's more adversarial in its mechanism. And also interpretability. Many people talk about interpretability, but in my opinion, this is a relatively subjective notion, because you may have your own criteria for interpretability. But for me, what I really interested in is actually, can we actually learn from the model? For example, we have this powerful GPT-3. Can we actually increase our knowledge, or can we actually infer something new? Can we have a new input from the model to linguistic, for example? Okay. Many people have worked on the theoretical aspect of deep learning, from different angles, and for me, I'd like to take the perspective of control. I think in the end of Winan's talk, he also mentioned that the perspective of control. We can look at deep learning from the continuum point of view, and go back to go down to the actual model with discretizations. Okay, I think this is a really nice perspective. I'm not going to talk about a theory, because most of the work are computation and application. But this perspective do shed a lot of light on how we actually combine a deep learning approach with traditional approach that we took to solve computation problems in inverse forward and inverse problems of PDs, and also inverse problem related to imaging and image reconstruction. Okay, so let me be a little bit more specific, and we can actually view deep learning, deep supervised learning, and also model-based reinforcement learning and meta learning, or some part of hyper network-based meta learning. You can put all together into this this a little bit messy, but it's a mean field control perspective, where you have your data X, sample from the distribution with the label Y sample from the distribution P, and it's actually go through a dynamic system that actually process your data, and in the end, it's get processed by another function G, which is the output layer of your network. Okay, and it matches with the data. Okay, so this is your terminal loss, and also and more often that you have this running cost as well. Especially for reinforcement learning. Okay, and this T is a continuum of your layer. Okay, and this U is the control parameters of your dynamics, which is a trainable parameters. And then we have three different regimes: the supervised learning regime, where we have this U parameter itself is a trainable, it's a control parameter, and sometimes U has this very specific function form where it depends on the state xt, and also it depends on some other parameters theta. And for typical type of meta control, where your control is actually controlled by another parameters. This is sometimes what they call that your parameter can be parameterized by another parameter. Okay, and it could take a more complex form. So this is the model side of it. And in terms of solver, you can use BP, or you can look at PMP, or you can use dynamic programming to solve a control problem. And this is the combination that we often see. From on the left is the model, on the right is the solver. But sometimes you see all the mixed matches, of model and algorithms. So the reason that I really like this perspective is if you think of most of our solvers for PD, or, inverse or forward problems, or image reconstruction problems, they're all iterative in nature. So they can all be viewed as either continuum or discrete dynamics. But what's different is that we rarely view them, well, at least in the past, we rarely view them as a control problem because the control parameter U are already designed by us. So we pretty much just design U, or we solve this control problem by our by us, right? And then we just evolve this dynamics. So now let's say that in your iterative process, there are some part of it, some mechanism that is not clear enough, or you can analyze it mathematically, but you know that the specific choice of this control should depend on data, but you don't know how to write a formula on such dependence. I think this is the part that it's perfect to use machine learning. This pretty much summarized the basic ideas of the two works that I'm about to show you. How to build in this machine learning mechanism into our traditional solvers, and hopefully we can improve our traditional solvers for some scenarios. Okay. And the reason that I call hyper networks in the title is because if you think of reinforced learning and meta learning, it's this dependence of the control parameters on another parameter theta, and also on the state variable xt, actually make this a hyper network structure. So if you write it in one of the simplest possible way to compare with the regular deep neural networks, and I call it meta, but it's really just a hypernet. Is that it looks pretty different, and I think for hypernet is that the control parameter, at least in general, it could be part of the control parameter, is determined by another network we call hypernetwork. Okay, this hypernetwork depends on the state, and it infers the weights that you're going to put on to process this x. Okay, in the next step. So it can be written into this form, and mathematically it looks different. Okay. And why do we need to consider this type of network? So first of all, there has been a lot of works on using hypernets. So I'll just give you a few examples. One of the earlier one is the dynamic filter network, which is basically from the name you can pretty much guess what it does. Is that it uses a network to infer the filters that you want to process your data. Okay, so the way that you want to process data is actually inferred by the network. So, sounds like attention, okay, but different in formulation. So basically, it's also feels like a self-training where you actually look at yourself, okay, and you try to figure out a way to improve yourself, okay. But the way to improve yourself depends on where you're currently at, okay. And you can use a hypernetwork to determine the depth. And this is one of our earlier work where when you do image denoising, and the depth or the stopping time when you evolve your algorithm pretty much is determined by the noise level, but you don't always know the noise level. So if you want to model adaptive to different level of noise, it's better to make the depth of your model or the loop time of your RNN depend on your input data. So this is actually what we do. We use a hypernetwork. We train it kind of like a reinforced learning, but we use a hypernetwork to look at the input, the output at each loop, at each iteration, and determine whether we should let it to iterate one more time or stop iteration. Okay, and also you can use this hypernetwork to determine some hyperparameters in your classical model. For example, you can this is what NUACID group did, where they use this hypernetwork to determine some of the tunable parameters or the hyperparameters that we normally tune by hand, but you can actually use a neural network to tune it automatically, and it has a very nice generalization property. Okay, and for the two of this for this work, you can actually see that this hypernetwork has superior performance in terms of auto distribution generalization. That means when your test data actually has a shift from your training data, okay, and if your model has this hypernetwork mechanism, but not always, but if you design it properly, and it has very good generalization or very good what we call OOD transferability. Okay, and there is a recent work using NTK to analyze this hypernetwork where you can actually see that you have a multiplication of two kernels, where you have this potential to actually improve for example, the condition number of your kernel. Okay. So now let me come back. This is a little bit detour, but let me come back to solving PDEs. And this is a highly incomplete list because for the past several years, about 3-4 years, there has been a lot of work on using deep neural networks to solve PDEs. Actually, before the boom of deep learning, people had already tried to use neural networks to solve PDEs. I believe from the 90s or maybe even earlier. I didn't look too further back. Okay, and roughly speaking, you can categorize the method into 3 categories. The first category is to use the neural networks as a new ansatz to approximate the solution. Okay, so basically, what we did in the past is that we approximate the solution U by using polynomial, using Fourier, using wavelets, using finite element. And it's natural to think, well, maybe we can approximate solution using neural networks, and this should be super effective in high dimension, and also in the cases where your PDEs or your boundary condition has solutions, or the boundary conditions has very complex geometries. Okay, so the most represented works, including Debris, Pin, and some other works along the line as well. Okay, and another class is to establish and approximate using deep neural networks to approximate the solution mapping. Okay, so it's essentially an integral operator, and the advantage, if you compare this to the advantage of for example, Pin, is that it's mesh free, so that you don't really have to establish a mesh. And that's why it works so well in high dimension, but you do need to retrain if you change the setting. For example, if you change the initial boundary conditions, and you need to retrain, and also if you solve a PDE in low dimension using neural networks at the new ansatz, its efficiency is one of the issue that people are still trying to resolve. Okay, because it's based on Monte Carlo sampling, and we know that it's hyper efficient in high dimension, but it's a suboptimal in low dimension. And for you try to approximate in mapping, that is the second approach. The advantage is that after you train, you can just use that during inference, right? It's super fast. Okay, but you do need to have a grid to start with. Okay, and the third approach, I really like it, is because it's for a lot of applications, finding a higher resolution solution for a PD is not the final step of the entire pipeline, right? You know, we find a PD, we want to do something about it, we want to analyze, we want to do some further computations, you know, afterwards, right? For example, to extract some physical quantities out of it. And if that's your final objective, then maybe you shouldn't spend so much time on finding a high quality solution, right? If your ultimate purpose, you know, your usage of the solution, you know, is very rough, is only, you know, for example, qualitative. So then maybe you can, you know, you can take full advantage of this end-to-end mechanism of deep learning, where you directly link your input and your final objective, your task. As long as the entire pipeline is differentiable, you can use backpropagation to train it. So this is the idea of the third approach, where you can establish, you can directly establish, you know, you know, some parameters of PD or initial boundary value, you know, condition of your PD to the final objective. You know, you skip the step of finding a solution, or you have your solution, your solver in the, you know, in the entire pipeline, but that's not the final the final destination. Actually, we have tried that in image reconstruction. We had a similar problem in imaging, because we always look at the PSNR or structure similarity, but for many applications, we want the image to do, for example, image recognition, and some other higher level task. And sometimes, you know, if you have your PSNR has 1 dB or 2 dB advantages, it may not matters in the end in terms of the task that you're interested in. Okay, so this is again, this is a very incomplete overview of the topic. So let me jump into the first work, where we try to use a deep reinforcement learning, you know, to connect the deep reinforcement learning with you know, with the PD solvers, where we specifically looked at is 1D scalar conservation laws. Very simple equations. We just want to see that you know, whether we can is it possible that we can get some potentials, you know, by combining a machine learning with a classical solver. Okay, so just a very rough introduction of reinforcement learning. Well, reinforcement learning is a very powerful tool, especially in the model-free scenarios where you don't really know the dynamics and you don't have an analytic form of your reward function, but you can still learn to make very good you know, decisions. Okay, so RL is to learn how to make a good sequential decisions, and the you know, basic model behind it is the Markov decision process. Okay, and before I start, I want to, because people always ask me, you know, why we use reinforcement learning rather than supervised learning. And later I'll show you some comparisons, you know, between the RL formulation and supervised learning formulation. I think for RL, it's actually quite it's natural to view our iterative solvers or any of your favorite iterative solvers. I think it's natural to view it as a sequential decision making, because well, the difference is that the decision has already been made by us. If you think of classical solvers, we already made decision for it. But like commented earlier, that if there are some components that you're not, you know that it's not optimal, or you know there are too many options, but you don't know how to choose, well, maybe it's good to view it as a Markov decision process, okay, rather than a Markov reward process. Okay, and also it's very flexible, and I think the second two are quite important. The third point is that if you train it, the policy, which is your decision maker, is non-greedy. It ensures a long-term accuracy rather than only look at the local, you know, approximations of your solutions. And also, this is also I mentioned earlier that it's a meta learning, like it has this hypernetwork structure, and make it you know, granted superior out of distribution transferability. Okay. So let's first look at, you know, how can we actually build this reinforced learning, you know, within a conservation law solver. We look at Wino, and this is a recall of how actually Wino does. And this pi is the key here, where it's the numerical flux, where we compute, you know, the numerical flux. This is in the finite difference setting. And this we designed this flux, this numerical flux as we use this the weighted average, to approximate, and with this weight sum into one. Okay, and we need to use this row speed to make it stable. But it's a relatively simple algorithm. But maybe for some applications the challenge is here that we know how to do this weighting in smooth regions, but in singularity, near singularities, we normally choose a very a relatively conservative way of choosing these weights, where we let this weight to approximate so that we know there is no oscillations. Okay, and also we do not know how to actually adaptive change, in terms of whether we should use Windows 5 or maybe sometimes Windows 3 is enough. Okay, there are a lot of options that you can think of. So you can actually make this if you view it as a Markov decision process, where you can actually use a neural network to make decisions for you. Okay, so you can let this pi f be a neural networks that takes these as the input, okay, the row speed, and also the current approximation of the fluxes as the input, and the action, okay, which is the output of the network, are the weights that you want to use. Okay, and you constrain them to sum it into one as well. Okay, and we have very simple state transition, because this is model based reinforced learning. Okay, and you can use a L infinity norm, the local L infinity norm as the reward. Okay, you don't have to worry about the differentiability, because in a way it's a derivative free optimization for reinforced learning. Okay, and you can what we did is we trained it on burgers with Windows 5 and Euler, forward Euler as the temporal discretization, and also with the specific delta x and delta t, and then with the terminal time t, which is point A. Okay, we use policy gradient to do that. Okay, and so we tested in three different scenarios, because we want to compare with some of the existing supervised learning method, and they're not that flexible. At least we didn't we didn't manage to train them on a setting that is different from their work. So we actually look at the three different scenarios in order to make a comparison. So the first scenario is in visit, where we don't have a viscosity and we don't have a force. Okay, and we generate random initializations. Okay, as the training data. Oh, by the way, the training data is generated using Windows 5, but with a much finer grid. Okay, so you can think of that as a true solution. Okay, and also with forcing, that means the initialization is 0, but we randomly generate different forces, and with viscosity. And also the vicious case, which is similar as the inviscid, but we have viscosity. Okay, so that means it's a with viscosity, but also with 0 force and randomly generated initialization. So these are three different scenarios, and we compared the RL Reno, we call it, as we call it, with a fifth order Reno, which is the baseline, and also with a work called L3D, which is work by Bar Sinai et al., which is published last year in PNS. Okay, and I also did a little bit comparison with PIN in our paper. Okay, what we found is that for L3D, basically they use end-to-end training and determine the approximation of differential operators. Okay, in the in the supervised learning fashion, which is not the hypernetwork fashion. It's as you can think it as a supervised learning SL control. And what we found is that if you train on one setting, so first of all, we found a trouble training the L3D on the setting that is different from their paper. So this is the setting of their paper, but the rest are not. Okay, so we put a question mark because we don't know how to tune their code properly. So we add a question mark here. Okay, may still work, but we just couldn't train it work properly. Okay, so if you use their training setting and try to generalize it, try to test it on other settings, we found that it actually failed. Right? It's sometimes you get in the end, sometimes you get a really big error. So this actually shows that using at least using this supervised learning based model, okay, it does not do very well in terms of out of distribution transfer. Okay, and also actually pin is actually quite flexible. You can actually use pin in a lot of this, but actually the training time is really large. Okay, comparing to other methods. Okay. So in terms of the RL Window versus Window 5, um, the circled region, this indicates our training setting, and all the others are actually the generalization to different delta X and delta T. Okay, it's slightly better because this is the measurement of relative L2 error on on everywhere. It's the entire spatial temporal domain. And the advantage of RL window is actually near singularities rather than this overall performance. Okay, so near singularities, these are these are two snapshots, and you can see that the orange curve is actually RL window, where it actually approximates the singularity actually better than window. And if these are just two snapshots, if you do a statistical analysis, you can see that the rainfall certainly doesn't really improve window in smooth regions. We basically separate the smooth and singularity regions. So you see that you do not see a benefit in smooth region, but you do see overall statistically you see improvement of RL in your near singularities. Okay. And by the way, this graph is a cumulative error, which basically means that if you read out this point, that means there are 200,000 points on the spatial temporal grid that has an error that is about 10 to the negative 3. Okay, so the closer the curve is to the right, to the left, the better is the method. Okay. And we're also curious on the actually the action that the RL take comparing with the human decisions. Well, the decisions made by window. If you look at what we can actually see that near singularities or in the relative smooth regions, what decisions are made are actually different between the two. We cannot really make a sense out of it. That means we don't really have interpretability of this method. But what we can observe is that RL indeed does something that is different from window. And overall, and especially near singularities, actually does better than window 5. Okay. All right, and for RL, it's because of this hypernet network structure, it actually generalizes pretty well. It can generalize to other fluxes, but if you give me a non-convex or even linear fluxes, it does not generalize that well or transfer that well. You need to retrain. So not so well on fluxes, but it generalizes across different settings and the different delta X and delta T, and also different viscosities and basically it generates well in terms of the parameters of your PDEs. Okay. So this is just a comparison of cross mode generalizing from inviscid to vicious, from forcing to inviscid and vicious as well. So I'll just skip the board presentation of the numbers. Okay, and we do have a comparison with L3D and P in our paper. So I'll just because of time, I'll just skip that. Okay, so the second part of the talk is to use meta learning or hypernetwork, to be more precise, to improve multigrid, and to improve multigrid in solving parameterized PDEs. So it's similar to the previous work. It's also a demonstration of the use of hypernetworks, in terms of OOD transfer. And for this, we want to be able to find a solver that works for parameterized PDEs where the parameter could vary in a fairly large range. Okay, so first of all, what's a parameterized PDE? Where you have this L is a differential operator, the U is your solution, and this ADA is the parameters that in your PDEs. It belongs to a certain range. It could be multidimensional. Okay. And one simple example is this steady state anisotropy diffusion equations, where your parameter eta is the basically it's the rotation theta, and also it's an anisotropy epsilon. Okay, so this is a linear, very simple example of a parameter PDE. Okay, so why should we care about parameter PDE? So where does this parameters come from? Where it could come from a lot of different sources. For example, it could come from the shape parameters, or it could be your material or property parameters. It could be your operation parameters like flight conditions and etc. It could be your initial and boundary conditions as well. Okay, you can encode your initial boundary conditions into these hyperparameters. Okay, and a lot of scenarios that requires you have a solver or efficient solver for your PDs for a wide range of ADA. Okay, for example, inverse problems, where if you want to solve inverse problem, you need to solve forward problems multiple times. And because of you're still adjusting your ADA during when you solve inverse problem, you adjust your ADA. Okay, so once you have an update on your ADA, you need to solve your forward problem to have your U and to match with the data so that you know how to actually adjust your ADA in the next step. Okay, so you need to repeat this solve U, but with ADA actually changing. So that's why you need to have a efficient solver for your forward problem. Okay, and there are many other examples as well. Okay, well, what you can do is if you discretize it, spatially, you can choose many of your favorite spatial discretization, and then you can cast it as a very high dimensional OD system. And one of the approach that people try to use is if you look at all of the solutions of a parameterized PDEs, you can think them as a structured a subset of in a very high dimensional space, and you can think it has a very low dimensional structure in a very high dimensional space, and you can use linear method like PCA to do reduced order modeling, or recently people start to use deep neural networks to do model reduction. Okay. But what we want to do is we still use classical solver, but we use machine learning built in to this classical solver to solve this parameterized PDEs. Where in our work we look at this steady state linear PD. So basically it's a linear system, but the system depend on a hyperparameter atom. Okay. So we know to solve this type of problem, multigrid is a very powerful tool. It has been very successful, for decades in a lot of branches in engineering and in science. Okay, but for example, for this anisotropic diffusion problem, where if you have an epsilon that is getting closer to zero, a typical standard multigrid algorithm will actually has an increase in its computation time or wall time. Okay, so both the vertical and the horizontal axis are actually in log scale. Okay, so what should we do to improve this? Okay, so there are a lot of components in multigrid that we can actually try to improve in a machine learning fashion. So if you were in Juncai He's talk, he mentioned MGNet, where it's also it's a way to view a multigrid algorithm as a deep convolution networks, and you can use that to do image clustering, to do all kinds of machine learning tasks as well. But in my talk, I'll mostly focus on solving PDs. Okay, so the components that you can try to improve is smoother prolongation restrictions, for example. Okay, and of course the question is, can machine learning really help to find to improve these components to solve PDs better? Okay, so but maybe the first question is how we can actually build in machine learning into this mechanism. I think this has already been done by Juncai He and Jinchao Xu in 2009, where they actually reformulate the multigrid into a feed-forward network, where we can actually view this as an optimal control problem, right? To properly write this into a deep convolutional network, you need to either view or rewrite the component into convolutions. And which can be done. Okay, I'll skip that, but just directly jump into the formulations of what we call PD MGNet, is because we want to use this to solve PD, so we added added prolongation and all the way back to the finer scales, and we use this residues to match to match data. Okay, and we do it in this specific way, is actually inspired by earlier work, I think by by Yingzhou Li and Jianfeng Lu, where we don't really need to have a lot of supervised data. We can just randomly generate F and try to find the UT, and that minimize this residual. Okay, so it's you can think of this as an unsupervised framework. Okay, and this a little bit messy looking network is just to explain how actually data actually processed into this network, and this actually makes this entire algorithm a deep convolutional network. Okay, so you can actually directly use this to solve parameterized PDEs by, for example, you can randomly generate a lot of ADA, and you can actually train your PD MG net on that. Or maybe you can, for if you know that you only want to use this solver on a specific given ADA, okay, or ADA doesn't really change much, okay, you can actually train it on this ADA. Okay, but of course, this may not be practical because in practice, this ADA often change a lot. So if it's based on the supervised learning model, when ADA change a lot, the distribution actually shift a lot, and it does not really transfer very well when the distribution shifts a lot. Okay, so I think the drawback is it has relatively poor generalization if you directly do it this way. Okay, unless you only want to use this model, for this ADA that is precisely the same as your training setting. Okay, so we decided to take a meta learning perspective. Basically, we view training a solver or learning a solver for a given ADA as a single task, and then learning a solver for a set of ADA. You can think of it as a multitask learning. And we know the reason that we want to view it as a multitask learning is because we can leverage common structures in this task, because for different ADA, even though your algorithm need to change a little bit, but this is still a problem of solving PDs. So there must be a lot of tons of common structures, and one of the most effective approach for solving multitask learning is meta learning, where we can roughly characterize them, classify them into two different approaches. The one is finding a good initialization for all tasks, and the representative work is mammal model agnostic, meta learning. But I think in an approximated sense, most of the meta learning can be viewed, or approximated using hypernetwork. Okay, so basically we, this hypernetwork takes the input that encodes the task. Okay, and for us, it's the input that encodes ADA or some quantities related to the ADA, and its output a appropriate control parameters and to the entire dynamics, and so that your entire dynamics is actually adaptive to different tasks, or for our problem, it's actually adaptive to different parameters ADA. Okay, so this is a connection that we draw, and with that, we can try to design a hypernetwork that does what I just described. Okay, so what we decided to improve is actually smoothing, and on the left, this is the regular smoothing. Okay, and this B is the smoother. You can actually approximate it using a convolution net. This is basically what MGNet designed. Okay, and this meta neural network is what we introduce, which takes the input of this ADA. Well, basically, it's the if you discretize because we're considering linear differential operator. If you discretize your linear differential operator using a basis that has some translation invariance, it can be written into this convolution form. So what we input is really just a convolution kernel, okay, of that differential operator with this parameter ADA built in it, and also the residual R. Okay, and it takes ADA and R as input, and the output, what it outputs is actually the smoother part. Okay, it could be the convolution kernels of your convolutional smoother, or it could be the column vectors which spans the the Krylov subspace that you want to do the subspace correction. Okay, so we actually in our paper we compared the two. I think the Krylov subspace version works better. So so let me explain that in a little bit further detail. So for Krylov subspace correction, so this is the definition of Krylov subspace. We just rewrite it a little bit. We just rewrite it as a function that takes A as input but this function is just a polynomial, okay? And it multiplies by the residual r. Okay, so we have r, ar, and a square r, and etc. Okay, so if we want to use a network that that infer a Krylov subspace, what can we do? Well, this is how we actually design it. This is a straightforward generalization from the classical Krylov subspace. So we use the neural networks to generalize this very simple operation, which is just a polynomial. Okay, and also we we use we also generalize this linear multiplication to a nonlinear operation. So that's how we actually generalize it. Okay, so we use this operator a eta as the input of a fully connected network, and this fully connected networks actually inference on the weights of a dense net. Okay, and then this dense net is operated on this R. So basically, this dense net is a generalization of this linear operation of this, a to the power of I multiplying R. Okay, and this fully connected network is a generalization of this function f1 up to fk. Okay, so this is design. Okay, and also we in our method we guarantee that there's always this R in this in this set of vectors, and so that you can still, similar as the standard proof for Krylov subspace correction, you can have convergence. It doesn't matter whether you train it very well. Okay, it's independent from the training of the algorithm. You can guarantee convergence and of the of the what we call meta MGNet. Okay, so a little bit numerical experiments. So again, let's come back to the 2D anisotropic diffusion, where we look at the in-distribution generalization. That means we for simplicity we choose angle theta equals to 0. Okay, in our work we have other numerical examples as well. So we let eta to vary well in the log scale uniformly between 0 and the -5. Okay, and we randomly generate 100 right hand side functions, and because this is pretty much the loss that that we try to minimize. Okay, so this is also the after training, and we apply it to it. Okay, and the stopping criteria of this once after training, the stopping criteria is that the relative residual is smaller than 10 to the -6. Okay, so if you look at the training distribution and also the testing distribution, they're pretty much from the same distribution. Okay, so we report the mean plus or minus standard deviation of the number of iterations, and also the computation time, or so the wall time, in order to compare the performance of different algorithms. So this is the list of a comparison. This is the what we propose, and this is a supervised learning based approach where we use this PD MGNet ADA to as some kind of baseline, because if you restrict your task, you simplify your task on just training a supervised learning model for ADA, and you only want to use that for that ADA as well. Okay, so this is the competition time of this. Okay, it actually took us a little bit by surprise that it even outperforms this setting, because for this setting it can only generalize. We train it on ADA, and we test it on the exact same ADA. Okay, it's not quite practical, but we just want to use them as the we at first we thought this could be the oracle, but it's actually outperformed this sort of oracle, is because we are actually treating this problem as a multitask learning. We can leverage the common structures into this multitask, so it can outperform the method where we only have this one task in mind. Okay, and comparing with this standard multi-grid method with Krylov type of smoother Gauss-Seidel and Jacobi, and then we also throw in this line Gauss-Seidel, which is actually specific designed for this problem when theta equals 0 and epsilon close to 0. Okay, of course we cannot outperform that, but this method is actually very, very limited. But we just want to it's just for fun to compare with this method. So you can see that overall we have a significant improvement in terms of speed and also number of iterations. So this is in distribution generalization. Okay, so this is actually a plot comparing, the degree of anisotropy and also the wall time, okay, in log scale of all of these methods, okay. And this curve is the meta MGNet. Okay, and we also look at the auto distribution transferability of the learned algorithms. So, well, of course, for all of these methods, there's no issue of auto distribution transferability, right? For classical algorithms, we shouldn't have that issue, and for this one, well, it's just we train on the ADA and test on the same ADA. Also, don't have that issue, and for this, we have this issue. If you look at it, it actually failed for multiple cases. Okay, but it's relatively stable for meta MGNet. Okay, so this actually shows that this hyper network actually grants a great auto distribution transferability, which is actually comparable to the classical algorithm. So that's why we think it's maybe a good idea to use hyper network and to improve part of your traditional algorithm, to have benefit. Well, the first benefit is that sometimes you can have a guaranteed convergence for this method, and also it may have a good transferability comparable to the classical algorithms. Okay, we recently we have another work on CT image reconstruction. It also demonstrates that that advantage, but I didn't talk about it in this in this work. Okay, in this talk. Okay, so let me conclude. Well, the first of all, you can regard discrete dynamics as some kind of convolutional neural networks, and you basically you can view deep learning as optimal control. Okay, and so that if you have your own dynamics that you designed in the past, but for some applications it does not work ideally, and precisely which component need to be improved, but you don't know exactly how to improve. Okay, that could could have a very complex mechanism, could highly depend on the data. Well, that's where you can actually use your deep neural networks to help you to improve that, and you can use control setting to actually train, do end-to-end training. Okay. So hypernetwork is a structure that leads to very good generalization, especially auto diffusion generalization. This, what we observed is only empirically. So as future work, we're trying to use this reinforcement. Basically, this reinforced learning approach is to view the iterative solver, your dynamics, as a Markov decision process, and try to make decisions. Try to make decisions based on data rather than based on purely based on human knowledge. Okay, so we want to do 2D or 3D, but because this is supervised learning scenario, so generate high quality mesh data in 3D is quite challenging, and we want to more aggressive policy, because right now we're very, very conservative. Basically, we stand on the shoulder of giants, and we only reach out a little bit further. Okay, so can we actually do this more aggressively? And also, can we actually do this with adaptive or moving mesh? It could be very helpful when you try to solve more realistic problems. Okay, and with this meta learning for multi-grid method, we want, for some problems it's more beneficial to learn prolongations and restrictions as well. Okay, and it's also more beneficial to generalize it to irregular grid. And we can think of using graph neural networks, but of course the challenge here is how do we make it insensitive to different type of meshes, especially the quality of the meshes. Okay, and maybe we can actually use this to improve learning other iterative numerical solvers with meta learning. So with that, I conclude my talk, and thanks for your attention.
Well, thank you. So I can read some of the questions that were posed here.
Yep.
So one is, can you talk about the training cost of the reinforced learning, and can your learning method generalize to different problem sizes?
I think a training, the very recent version of reinforced learning, because this is 1D problem, and I think we have reduced it from 1 or 2 days to hours. But again, this is not a very large sized problem, and it can generalize to different mesh sizes. I don't know whether that answers the question. You train it on a specific given size, and you can generalize on different settings of your delta x and the delta t. Okay, um, and but it does not really generalize very well to different type of fluxes. So we only managed to generalize to this one, but we tried linear and a non-convex version of it. It does not. Okay, so it's still generalized, but it does not outperform Wino. So yeah, I don't know whether that answers the question. If not, you can follow up. I'm sorry. Yeah.
Right. Thank you. So another question is this. For non-symmetric systems, Krylov space solvers generally do not converge to the correct solution. Will the convergence guarantee statement of MGNet hold?
For the
Non-symmetric
non.
system is talking about Krylov space solvers. I don't know if you tried this.
Well, okay. So first of all, well, okay, I don't know the answer to that because I'm not really the expert. I think maybe Jinchao Xu, Professor Xu can answer that. But the proof is pretty much the same as the proof for the Krylov subspace. So if you have trouble converging for the non-symmetric case for the standard Krylov subspace, I don't think this machine learning can help you. At least not theoretically. What machine learning can actually help is that if you have a guaranteed convergence, but in practice you do not how to actually pick an optimal subspace to improve your speed. Well, machine learning can actually help you to select within this range of converging region how to actually should pick your subspace. But if your original proof had trouble, well, at least I don't know whether machine learning can actually help you with that. Jinchao, Professor Xu, you want?
Yeah, Krylov space, that's right. It doesn't usually converge for non-symmetric problem, but it does. Sometimes, for example, you can say the symmetric part is definitely there are special cases that you can prove that. But anyway, maybe this machine learning can actually learn the way through that. Maybe you can actually do better than the linear situation. We don't know. Maybe this is probably a good point we can try.
Yeah.
Because you do have the flexibility to have to actually learn from many different data to try to make it work. But if you talk about proof a theorem, it's just difficult to prove it, I suppose. Yeah. But I think algorithmically, it's probably a chance to be. I wouldn't be surprised to be better than the linear solver you usually have. That's very
at least point. We can try. Yeah, at least empirically we can try it.
Yeah, right. Theoretically, it's always hard.
Yeah.
Okay, maybe I can read one last question, and it's: is there any theoretical interpretation about the dense net-based neural network which is used as a smoother? Can this neural network really recover or approximate some efficient classical smoothers, such as line smoother for anisotropic problems?
That's another very tough question.
Yeah. Can you think it as smoothers?
Well, I don't know. It's well, at least in our setting, we cannot really, for example, line smoothers. It's nowhere close to the line smoother. So I guess it's unless you design a loss that specifically guides your. Okay, so the loss here is pretty much just at the end of the result. It's the end-to-end loss. It's at the end of the algorithm. If you add a running cost or intermediate loss that specific guides your this meta this hypernetwork, maybe you can try to let it approximate something that you want. But maybe you shouldn't hope that it actually, miraculously recover some of the known smoother by having only the the end-to-end, the loss at the very end of this deep network. Yeah. Professor Xu, you want to?
Yeah, this line smoother is very, very special smoother, and that only works that the anisotropic direction line up with the grid. And in that particular case, the line smoother works. If there's orientation, if the anisotropic doesn't line up, basically there's no line smoother exists. It doesn't really work. So now if you come back to this idealistic situation, actually lots of paper written in multi-grid on these things, the line smoother. So now it depends on where you start from. If you suppose, if you think about a multi-grid smoother as a convolution, it depends on the size of the kernel. Yeah, we actually tried if the kernel is big, you want to train the kernel that way, or if you took a full size, for example, you will get the line smoother out of it. Anyways, you can train the line smoother, yes, from the, but again, that's a very specialized one, which is difficult to generalize. And we just don't know when this theta is not equal to 0, maybe 30 degrees or something, this thing is getting more interesting. And the answer is that, so the line smoother, if you have the a priori analogy, somehow you just pretend you don't know the line smoother, you can learn out of it. But in general, it's the line smoother simply doesn't work if the anisotropic doesn't line up the grid. That's the maybe the comment I.
Okay, well, thank you. Then I would like to thank all three speakers of today. And well, we conclude here, and we'll meet again tomorrow morning. All right, thank you.
Thank you.
Thank you.